So basically, when we talk about relations, so in relations we have a set A, it is a non-empty set, and it is mapped to another set, same set A. Suppose here we have 1, 2, 3. Here also we have 1, 2, 3. Now, if you do the mapping, you can do this type of mapping, like 1 is mapped to 1, or 1 is mapped to 2, 1 is mapped to 3, 2 is mapped to 1, 2 is mapped to 2, 2 is mapped to 3, 3 is mapped to 1, 3 is mapped to 2, 3 is mapped to 3. So these are all the possibilities which are possible, all the type of relations. But if you talk about a particular relation, suppose we are talking about a relation R is equal to x comma y such that x is less than y and x comma y belongs to A. So this relation we are talking about. So if we are talking about this relation, this is called set builder form. Okay, this is the rule method. The rule is given. Now, if you want to write it in tabular form in terms of elements, so you take suppose 1 from here. This is x. Okay. So 1 is less than which number from this? So 1 is not less than 1, obviously. 1 is less than 2, 1 is less than 3. So one pair will be 1 comma 2, 1 comma 3. These two pairs will be there. Now if we come to 2, 2 is now x. 2 is less than neither 1, neither 2. It is only less than 3. So 2 is less than 3. 3 is not less than any one of them. So it will be not mapped. So this is this relation. So this relation here is, is having how many elements? 3 elements. And these 3 elements are from here only. 1 comma 2 from here, then 1 comma 3 from here, and then 2 comma 3 from here. So these elements it has taken from this universal set. Now the relation could be something else also. Suppose R is a relation. Now R1 is a relation x comma y such that x plus y is greater than equal to 2 and x comma y belong to A. Now first write till here, then I will ask from you what will be its tabular form. Have you understood this?
Yes, sir.
Okay, first write till here. Okay, so I hope you have written it. Now I want you to write this relation R1 such that x plus y is greater than equal to 2. So if you see the elements here, so let if you see these elements, actually what is happening here, that if you add x and y like 1 and 1, it will become 2. And other numbers like 1 plus 2 is 3, 1 plus 3 is 4, likewise. So all the numbers in this set will be taken into account in R1. We can take 1 1, we can take 1 2, we can take 1 3, because addition of both of them is greater than equal to 2. Then we have 2 1, 2 2, 2 3. Then we have 3 1, 3 2, 3 3. So this is called universal set, universal relation. The relation which comprises of all the mappings. This is a universal relation. It is having all the mappings. And if I give you a relation R2 such that x comma y, such that x minus y mod is greater than equal to 3. Okay. Now I'm giving you this condition. X minus y mod is greater than equal to 3. So here, if you see 1 minus 1, it will be 0. It is obviously not greater than equal to 3. 1 minus 2. 1 minus 2 is minus 1. And mod of minus 1 is 1. It is also not greater than equal to 3. 1 is smaller than 3. 1 minus 3 is minus 2. And mod of minus 2 is 2. 2 is also not greater than equal to 3. It is less than 3. Then you have 2 comma 1. So 2 minus 1 will be 1. It is not greater than equal to 3, less than 3. So you can see all the elements here. If you take x minus y, you will find that none of them is greater than equal to 3. No pair is there. So you say that this R2 relation is a null relation. So we say R2 is a empty relation. So these two are extreme cases. One is empty relation, null relation, another is universal relation. All other relations will come under the category of these two extremes. Okay, like if I take R3 relation and I want to ask you that x comma y such that let us define like this time, let us take we can take any relation. Like if you also want to think of any relation, you can tell. So I'm thinking of taking a relation x into y is x into y, the multiplication here is less than equal to 4. So here 1 comma 1 will be there. 1 into 1 is 1, which is less than equal to 4. 1 comma 2 will be there. 1 comma 3 will be there, because 1 into 3 is 3, which is less than equal to 4. 2 comma 1 will be there. 2 comma 2 will be there, because 2 into 2 is 4, which is less than equal to 4. 2 comma 3 will not be there. This 2 comma 3, this will not be there, because 2 into 3 is 6 and 6 is not less than equal to 4. So that we eliminate. 3 comma 1 you can take from here, that is 3. Again 3 comma 2 you can't take because it is 6. 3 comma 3 you can't take because it is 9. So they are greater than 4. So 3 comma 1. So another element which comes is 3 comma 1. So this is also a relation. It consists of 6 elements of the universal relation. So write these also starting from here. Write this one also, the R2 relation. Now, if you want to find out that how many relations are there, okay, like for a set A, which is having suppose n elements, okay, there is a set A which is having n elements. It is having n elements, A1, A2 till an. So, how many elements are there in A cross A? So A cross A, that means you are mapping each element of A with each element of A. Okay. So that will be n into n. Okay, that is n elements in A into n elements in A. That is n square. For example, here in this example, how many elements were there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So number of elements in the sample space was here 3 into 3, which is 3 square, which is equal to 9. So there were 9 elements. So if you have any set A which is having n elements, then it's A cross A, that is the Cartesian product. This is called the Cartesian product that we have studied in 11th. So that Cartesian product will have n square elements. How many relations can be made from this? How many relations can be made, can be constructed from A to A? So if you try to understand that this A cross A is having how many elements? It is having total n square elements. And a relation, basically, this is a very important point, that a relation is a subset of A cross A. As you can see in the above example, whatever relations we have taken, okay, like we have taken R relation. So this R relation was having element from this S only. It was a subset of this S. R1 relation, this was exactly equal to S. So it is a improper subset, but it is a subset. R2 is an empty relation. It is also a subset. And R3, it is having 1, 2, 3, 4, 5, 6 elements. And it is from here only. So it is also a subset. So this S is nothing but A cross A. So this all the relations which we get are actually the subset of the Cartesian product A cross A. Now you have studied, if you remember in class 11th, for a set A with m elements, number of subsets can be 2 to the power m. Okay. For example, this is a very famous example. Suppose we have 3 elements and we talk about all the subsets. So one will be null set, another is only having 1, only having 2, only having 3, another is 1 and 2 and 1 and 3 and 1 and 4, 1 and 2 and 3, sorry, 1 and 4 nahi. This is 2 and 3, two elements combination, and another could be all 3. So how many are there? 1, 2, 3, 4, 5, 6, 7, 8. So number of element in S was 3. Number of elements, number of subsets. This is number of subsets of S is equal to 2 cube, which is equal to 8. So that is why this formula is there, 2 to the power m. Now, if we say that relation is a subset of A cross A, relation is a subset of A cross A, and A cross A is having how many elements? A cross A is having n square elements. So it means that number of relations which are possible is equal to 2 to the power n square. Okay, it is 2 to the power n square. This is a formula which is very important. Remember this formula, especially for competitive exams. It is very helpful. If you want to find the number of relations which are possible from a set A to a set A, where number of elements in set A is equal to n, then this is the formula. So you can start writing it from here and try to understand it also while writing it. Okay. It is very important. If you don't understand any step, you can ask me. I will explain it again. I will give you a simple example. Okay. So have you understood this part while writing this part, Muhammad Ali Muhammad? Have you
Sir,
understood this part?
yes, sir.
So I'm moving it down. From here, we have recapped whatever we have studied in 11th. This is a recap that how many subsets we have actually for a given set S. So this is a formula. So now if I give you a question that it says, for example, there is a set A which is having two elements. So how many relations can be there of A cross A, from A to A, let us say, of A cross A instead of that, from A to A. So can you tell me the answer?
16.
Sorry, Ali.
16.
N.
No, 2 to the power n square, right?
Yeah, 2 to the power n square. So what is n here?
N is 2.
N is 2. So it will become 2 to the power 2 square.
Yes.
What will be this equal to?
16.
16. 2 to the power 4, which is 16. Right. So this is how we can apply this. Now let us talk about few types of relations. There are three types of relations. One is called reflexive relation. Reflexive relation means that A comma A belongs to the relation R for all A belongs to the set A. For example, if we have a set A which is having element A, B, C. Now I'm taking A, B, C. Okay. 1, 2, 3 we have taken. So I'm for a change taking A, B, C. So if you take a relation R such that A comma A and A comma B and B comma C and B comma B, like this. So if it is asked that is it symmetric relation? So what does, sorry, is it reflexive relation? So what does reflexive relation mean? That A is mapped to A for all A belonging to A. So here there are three elements, A, B and C. So A should be mapped to A, B should be mapped to B and C should be mapped to C. So A is mapped to A and here B is mapped to B, but nowhere C is mapped to C. So we will say that this is not reflexive relation. If we have some another relation, suppose U relation, which is having A comma A and A comma C and B comma B and B comma C and C comma C, suppose. So these type elements we have taken. Here, if we observe, here A comma A is also there, B comma B is there, C comma C there. So this is a reflexive relation. So if you want a relation to be reflexive, it is important that all the elements of the set is mapped to itself. Okay. And if you want to suppose take a mathematical example, another example could be like you take a set A with elements 1, 2, 3, suppose, and S is equal to x comma y such that x is less than equal to y. Okay. Where x comma y belongs to A. So you don't have to write all the elements. Okay. You don't have to write all the elements. You just see that if we take x comma x, like 1 comma 1, 2 comma 2, 3 comma 3, does it satisfy x less than equal to y? So if we take x comma x, x is also x, y is also x. So does it satisfy x less than equal to x? Can a number be less than equal to itself? Yes, it can be equal to, of course. So equal to is of course there. So we can say yes, it is reflexive because all of its elements will be mapped to itself. If suppose it was only less than, not equal to, then it will not be reflexive. So we say yes, it is reflexive. So first write this type of relation.
Sir,
Yes.
I have one question.
Yes.
Sir, but in there it is saying that S is equal to X comma Y, right?
Huh? Yes, right.
But then why did we take X comma X and not X comma Y?
Because what we are doing here is, this is set A, right? This is set A, which is having the element 1, 2, 3, right? We
Sir,
are taking X from A, Y is also we are taking from A. So this another set Y both is from A. X, Y both belong to A. So if I want to check reflexive, what we have to check is that A comma A belongs to the relation. That is, a number is mapped to itself, or a value is mapped to itself. So if we are comparing 1 to 1, 2 to 2, 3 to 3, that means we are taking the, one second, we are taking the element, which whatever element we are taking from set A, that is X, same element we are taking from this set A, which is Y. So both is X, because here it is mentioned, na? We can take Y equal to X also, and Y cannot be also equal to X. But for reflexive, A comma A should be there. This is very important. Both will be same. So if both will be same, then we take X comma X. And we know that X is equal to X, a number is equal to itself. So less than equal to is automatically satisfied. So we say it is reflexive. I hope it answered your question.
sir.
Now you can write it from here. I am scrolling it down now. So what we are checking here, that 1 comma 1, 2 comma 2, 3 comma 3, are these present in that set? So we know that 1 is less than equal to 1, 2 is less than equal to 2, 3 is less than equal to 3. So yes, 1 comma 1, 2 comma 2, 3 comma 3 belongs to the set S. Okay. So this is an extra explanation. If you want to write this, you can write it. Otherwise, you can just write till here and it is fine. Now, next is symmetric relation. Next is called symmetric relation. Symmetric, as the name suggests, As we know, symmetric means similar from both the sides. This is what symmetric means. So if we have an element A comma B belongs to the relation R, that is A is mapped to B, then B comma A must also belong to R for AB for R. If A comma B belongs to R, then B comma A also belongs to R for R to be symmetric relation. And what is AB? AB is where AB are elements of the set capital A, the set which we are talking about. So for example, if we have a set A, I am again taking suppose 1, 2, 3. Now let us take 4 also for a change. And if I take a relation R1 where I am mapping 1 with 1 and 1 with 3 and 1 with 4 and then 2 with 3, then 3 with 2, then 4 with 1 and then 4 with 4. Okay, we are taking like this. Now, here the question is whether it is symmetric or not. Is it symmetric? So for symmetric, what we need to check that if A comma B belongs to the relation R, then its inverse, that is if you change the order, then also it belongs to the relation R. So 1 comma 1 you don't have to check because both is same. 1 comma 1 and its opposite 1 comma 1 will be same. 1 comma 3. So if 1 comma 3 is present in this relation R1, is 3 comma 1 present in this relation R1? You can see that nowhere 3 comma 1 is present in the relation R1. So here itself it showed that it is not symmetric. But let us see further also. 1 comma 4. 4 comma 1 is there? Yes, 4 comma 1 is there. So because of this, it is okay. 2 comma 3 is there and 3 comma 2 is also there. This is also okay. And this is 4 comma 4. This is same. So due to 1 comma 3, we don't have 3 comma 1. And it says that if A comma B belongs to R, then B comma or A must also belong to R for R to be symmetric relation. So here it is not symmetric because 1 comma 3 belongs to the relation R1, but 3 comma 1 does not belong to the relation R1. 3 1 comma 1 is not present there. But if we take a relation, suppose R2, and we do there one thing that we take same elements, these elements which we have taken, like 1 comma 1 and 1 comma 3 and 1 comma 4 and 2 comma 3 and 3 comma 1 and 3 comma 2 and 4 comma 1 and 4 comma 4. So I have added one element here, that is 3 comma 1. So if 1 comma 3 is there, 3 comma 1 is also there. Rest are same. 1 comma 4 is there, 4 comma 1 is there, 2 comma 3 is there, 3 comma 2 is there, and 1 comma 1, 4 comma 4, it is obviously same. So we say that here R2 is a symmetric relation. So R2 is a symmetric relation because for all A comma B belongs to the relation R2, B comma A also belongs to the relation R2. Then B comma A also belongs to the relation R2. Now another example which I'm going to take is this one. A is 1, 2, 3 and this S relation is x comma y such that x is less than equal to y where x comma y belong to A. And I want to check whether this is symmetric or not. First write till here, then I will come to that. There is one more thing. There is another way also to make this symmetric. This one way I told you that 1 comma 3 was there, so I included 3 comma 1 also. Another way could be there, that we can remove this 1 comma 3. Then it will become symmetric, because 1 comma 3 is not there, so we won't check 3 comma 1. 1 comma 4 is there, we'll check 4 comma 1. 2 comma 3 is there, we'll check 3 comma 2. If something is not there, a comma b is not there, then we won't check b comma a. So that is also you need to understand. So that there, in that manner also we could have make it symmetric. I was scrolling it down. So now I was talking about this relation. A1 2 3, S is x comma y. A is 1 2 3, and a relation S is there, which is x comma y, such that x is less than equal to y, where x comma y belong to the set A. Okay. Now just think little bit about it and tell me whether the relation will be symmetric or not. If you want to write the elements of that relation, you can write it. Okay. And then see, try to find it out. And if it is symmetric, what is the reason? If it is not symmetric, then what is the reason? So Ali, can you first tell the elements which will be there in S?
1 comma 1, 1 comma 2,
Sorry, 1 comma 1, 1 comma 2.
1 comma 3,
Okay,
2 comma 2,
okay,
2 comma 3,
okay,
3 comma 3.
okay. So reflexive it is there. We have already checked earlier. 1 comma 1 is there, 2 comma 2 is there, 3 comma 3. Now question is whether it is symmetric or not. So can you tell whether it is symmetric?
No, sir.
It is not symmetric because 1 comma 2 is there, but 2 comma 1 is not there. And 1 comma 3 is there, 3 comma 1 is not there, 2 comma 3 is there, 3 comma 2 is not there. And it is obvious, even if you don't write this element, you know that if x is less than equal to y, then y is less than equal to x. It is not necessary. They can, it is only possible if x and y are equal, like 1 comma 1. So any order you write, you whether write the second one first or first one first, they are equal. It is only possible if x is equal to y. Otherwise, if x is not equal to y, then either x is less than y or y is less than x. Both can't be possible. One number is smaller than another, then another number is also smaller than the first. That is not possible. So we say that this is not symmetric. Okay, so write this one. You can write one more sentence here, like if x is less than y, then, sorry, if x is less than y, then y is not less than x. Less than equal to also you can write. Now, third relation, type of relation, there are three types of relations. First, we have seen reflexive. Second, we have seen symmetric. Third is transitive. So, what is this transitive relation? This was second one, right? This transitive relation is that if we have A comma B belong to the relation R and B comma C belong to the relation R, then here it is if this is belonging to the relation R, this is belonging to the relation R. So here the second element B and here the first element B are same. Okay, that is important to mark. Then if A comma C also belong to R, that is the first element of the first pair and the second element of the second pair, if that is also belonging to the relation R, then we say then the relation is transitive. So if we see an example, suppose A is 1, 2, 3. I'm taking the same example. No, right now I'm not taking the same example. I will take that example also, which we have discussed in above two cases. But before that, let me take this. 1 comma 1 is there in the relation. 1 comma 2 is there in the relation. 2 comma 1 is there in the relation. 2 comma 3 is there in the relation. 3 comma 3 is there in the relation. Now, if you observe here, we are talking about right now transitive. So in transitive, what we check that if A comma B belongs to R. So let us talk about 1 comma 2. This belongs to the relation R. Is 2 somewhere else also in the first element? Here it is there. 2 comma 1. So 1 comma 1 should also belong to R. So yes, it is there. So it will always happen. If A comma B is there, then B comma is A is also there, then A comma A will be there. So for that, we don't have to always check. So for this, it is okay. Now we proceed further 2 comma 3. So 1 comma 2, it ends with 2 and here it starts with 2. So 1 comma 2 belongs to the relation R and 2 comma 3 belongs to the relation R. Then what we need to check? We need to check is 1 comma 3 also belonging to the relation R, that this first element of the first pair and second element of the second pair 1 comma 3. Does this also belong to the relation R? But you can't see it is anywhere in this relation R. So you will say no. So it is not transitive. Now, if you do one thing, suppose if you want to write this relation R1 is, you make it 1 comma 1 is there, 1 comma 2 is there, 2 comma 1 is there, 2 comma 3 is there, and you include this 1 comma 3 also, and 3 comma 3 is there. So this 1 comma 3 I'm including. Now, is it transitive? So if we check others also, is there any possibility in others? So 1 comma 2 we have done, 1 comma 3 I've included, 2 comma 1 and this 2 comma 1 is there, and this is 1 comma 3. So it ends with 1, it starts with 1. So then 2 comma 3, is that 2 comma 3 also there? So yes, 2 comma 3 is there. So this is also done. 1 comma 2 was there, 2 comma 3 was there, then 1 comma 3 was also there. Okay, 1 comma 2 and 2 comma 3. Then we have 1 comma 3. Next is 2 comma 1 and 2 comma 3. So we have, sorry, 2 comma 1 and 1 comma 3, 2 comma 1 and 1 comma 3. Then we have, does we have 2 comma 3? So this also we have. Now 1 comma 3 we move to. So 2 comma 3. So it ends with 3 and this is 3 comma 3. So this is obviously 2 comma 3 is already there. 1 comma 3 will come. It is again 1 comma 3 is there. 3 comma 3. So it will become 1 comma 3. For 3 comma 3, none is starting from 3. So it is okay. So now we say yes, it is transitive. So we have to see all the possibilities, not only one possibility. If any one possibility is not there, then we'll say that it is not transitive. So write this first, then we'll see the above example also. I'm scrolling this down. So the above example, that is x less than equal to y. Okay, I'm leaving it for you as a homework. Then I will discuss in the next class. So you have to find out that whether if we have a set A which is having element 1, 2, 3, this is a homework, and there is a set R such that x comma y such that x is less than equal to y, x y belong to A. So can we say that is this relation? You write the elements and then see. And even if you don't write the elements, then also you can check. Okay. So is this relation transitive? That you have to do as a homework. So we keep till here in today's class. Okay. And we'll meet again soon. Anything you want to ask, Ali?
Sir.
Okay. Write this down. Just write this down.
Done, sir.
Okay, so I'm concluding the session now. Thank